first, just to kind of recap some of what we already know that's not gonna change for us this time. I'm gonna look for the first derivative, sign chart and all that. The first derivative will help me figure out where a function is increasing or decreasing. And if I make a sign chart, also I could use that first derivative to figure out if I have a max or any maximum or minimum values. The second derivative will tell us whether the graph is concave up or concave down. And we can use the second derivative to find inflection points. We can also use the second derivative to help us figure out if a critical value is a max or a min, right? Because it's concave up at a minimum, it's concave down at a maximum. That doesn't change. So what we're going to do now is just, because the types of functions that we're looking at, rational functions. So basically we're allowing for x's in the denominator. In the last section, we focused exclusively on polynomials. So now, if I allow for the possibility that x appears in the denominator of a fraction, there could be domain issues, right? So when we're doing curve sketching, we're going to figure out what the domain of that function is. Also, we can get odd, like weird behavior of a graph as x gets close to a value that might make us divide by 0, right? So like when we're looking for a domain, like with rational functions, we're basically just looking for, okay, can't divide by 0. What makes me divide by 0? Just throw that out of the domain. And the domain is everything else. But when we get close to those values, we get weird behavior, and we often get these vertical asymptotes, which kind of, I'm just going to make this up, but like let's suppose, I had something, 1 over x minus 1. There's a rational function. I got x's in the bottom. X obviously can't equal 1. And the kind of behavior that we have around those is this sort of behavior here where the graph like either shoots upward toward infinity or downward towards negative infinity. And we can kind of see why, because in this case, it's a simple case, but like if the numerator is fixed and I get closer and closer to dividing by 0, like 1 divided by 1/10 is 10, and 1 divided by 1/100th is 100. Like the closer I get to 0, the greater, the bigger these numbers are. So we get that kind of interesting behavior in the graph around these places that are not in the domain. So we're going to find intercepts. That usually, this part doesn't require calculus. Like if 0 is in the domain, plug it in, get the Y-intercept. If we can, we'll figure out if there are any X-intercepts. If there are any X-intercepts, right? There may not be. For example, if our graph is if our function is 1 over x minus 1, that's never going to be 0, because a fraction is 0 precisely when the numerator is, and 1 not equal to 0 ever. So we can do some stuff that doesn't require calculus. Then we get our derivative information. And then this part here, this is new in this section. So determine the behavior of the graph as x becomes large. With a regular polynomial, the behavior of the graph as x becomes large is always the same. It just sort of continues up forever or continues down forever. And now that can still happen in these rational functions, but sometimes we also get like a leveling off behavior. Like, for example, 1 over x minus 1. As x gets huge, this thing just sort of gets really small, right? And in order to figure out what that behavior is, we evaluate the limit as x gets huge. If we find that that limit is a constant, then this horizontal line, like y equals whatever that constant is a horizontal asymptote. Like in this case, 1 over x minus 1, like y equals 0, that's a horizontal asymptote. This line that the graph just keeps getting closer to doesn't actually become 0. That's okay. But it's what it approaches. Sometimes, and this is going to seem weird, it either approaches some constant, like a fixed number, or it might approach infinity or negative infinity, but sometimes what we're interested in is learning how it approaches infinity. So sometimes when we evaluate this, it's not just that I want to know, oh, does it blow up? But in some cases, when we evaluate this limit, we'll be like, yes, it blows up, but it blows up in precisely the same way that this line blows up. And we kind of get this slant asymptote that it approaches. And we'll see an example of that in either our first or second example in this section. And then the last part is the same. We kind of summarize in that table, write down our conclusions and use it all to sketch, put it together. So we're going to do a couple of examples. So we're going to sketch a graph of this function. 8 over x squared plus 4. So I'm going to do some of this stuff I'm going to do some of this introductory part in the top margin. We're going to need some space, you guys. The first thing, what's the domain of this function? What is it that we have to be on the lookout for?
X equals 2, or x equals minus 2.
So if x is equal to 2 or minus 2,
Oh, no, it'll be 1, that's not.
then x squared is 4, positive 4, yep.
Just become.
So, but what you're getting at is that you're trying to look for things that might make us divide by 0. Are there any values of x that'll make this x squared plus 4 equal to 0? Yeah, no values. So since x squared plus 4 is not equal to 0 for all x, that means that the domain is all real numbers. Now, what about intercepts? Is 0 in the domain?
No.
Why?
Well, that means I'm wrong.
Not necessarily, but didn't we just say what the domain was?
All real numbers.
Is 0 a real number?
Yeah.
Yeah, we can plug that in. Am I allowed to plug in 0? Yeah, there's no problem plugging in 0. 0 is in the domain, so the y-intercept, we set x equal to 0, and we get y is equal to 8 over 4, which is 2. So that means that 0, 2 is the y-intercept. How do I find x-intercepts? Yeah. So let's set y equal to 0. So that gives us the equation 0 equals 8 over x squared plus 4. When does that happen? At 8? So if x is 8, 8 squared is 64 plus 4. We get 8 over 68. Not equal to 0.
So there is none?
Why?
Because you can't set it equal to 0.
Well, we can set it equal to 0, but it's just there's no solutions to this equation, right?
Yeah, that's what I meant, sorry.
Yeah. No, you're right.
What was that?
Oh, because yeah, 0 doesn't equal 8.
Because what?
0 doesn't equal 8.
0 doesn't equal 8, right? A fraction is 0 precisely when the numerator is 0.
Like a half.
8 not equal to 0. Yeah. So this never happens. So that means that there are no x-intercepts. So far, what we know about this function is that it goes to the point 0, 2, and that's it. So let's maybe try to get some more information. The next bit of information we need is the derivatives. So let's start on that. So if I'm going to find the first derivative, what would be a helpful way to write this function?
8 times x squared plus 4 to negative 1.
Yeah. Look, there's no x up top, so it's absolutely like much easier on us if we bring that up as a negative 1 power, because then I don't have to use the quotient rule, right? And it doesn't, or the product rule. So when we find this derivative, we bring the negative 1 down, we get negative 8. Then we have x squared plus 4 to the negative 2nd power. And then the chain rule says I have to multiply by 2x. So we get negative 16x. I'm going to go back to fractions. Negative 16x over x squared plus 4 squared. Now we are going to definitely find the second derivative as well, but let's just sort of sit on this for a moment. Do we have any critical values?
The 4 squared.
The 4 squared? Like, you mean if I plug in 4 squared, that'll make this 0? No. No.
X is equal to 0 on top.
Yeah.
Make it 0.
Yeah, that's so critical values are where the first derivative is 0 or undefined. So I would be looking for what makes it 0 for sure is x equals 0. I would also be looking for is there anything that makes me divide by 0, but again, there's not because x squared plus 4 is always positive. So yeah, we have one critical value at x equals 0. And this sign chart is going to be pretty simple to make. I got one point of interest at 0. I'm going to have a row for negative 16x. I'm going to have a row for x squared plus 4 squared. And then I'll have a row for y prime. Now, they're not, the top, that minus 16x, that's a linear factor, that I'm looking at. But the bottom is not linear. That's okay. Like, usually I'd have to be a little bit careful about that if I have like a quadratic factor. Because, quadratics can be 0 in more than one spot. But like this, we've already observed is all positive, right? This is super extra positive. I'm taking something that's already positive and then I'm squaring it, right? So this row is easy to fill in. That top row is 0 at 0. And then be careful with this sign. It's a negative 16x, so it's actually positive on the left, negative on the right. And then this is 0 when x is 0. We've already observed that. But I just want to point out something here. This sign chart we're making in much the same way. Before, when we were just looking at polynomials, we just wanted to make sure we factored everything. Here we're factoring. We want to make sure everything's factored in the top or the bottom, and it is. There is no factoring for us to do. But we make a row for every factor that appears up top or on the bottom. And you have to be aware of that, like when you're using your critical values. This is something that makes the derivative 0, not undefined. That's like a distinction you want to be able to make. And then we just fill in our sign. So it's positive over here, negative over there. Now, to find the second derivative, we kind of are stuck with using the quotient rule or the product rule if you want to, write that as a negative second power. I'm just going to go ahead and use the quotient rule. So the quotient rule, that's the one that goes g f prime minus f g prime over g squared. So g f prime, so that's x squared plus 4 squared. F prime is negative 16 minus f negative 16x g prime. So the derivative of that x squared plus 4 squared is 2 x squared plus 4 to the first times 2x. And then this is all over g squared. So it's going to be all over x squared plus 4 to the fourth. How's that so far? Okay. Let's do some simplifying because so here's why we'd love to simplify. I cannot make a sign chart for this right now, right? It is useless. Like, this does me absolutely no good. So let's simplify. We could take out an x squared plus 4 they have in common and a 16 they have in common. So if I take out a 16 and an x squared plus 4, what do we need in order to get us to that first product there in the top? What?
X squared plus 4 and negative 1.
Mm-hmm. Good. I'm going to go ahead and just make these both positive, right? We're subtracting a negative. And then, so I'm bringing that plus down. And then, what do we need in order to get us to that product?
4x.
We need 4, I think it's 4x squared, because,
Oh, because you had the 16, so yeah.
Yep. Because, yeah, that was a 16x. So I have 2 factors of x there that we have to pick up, and 2 factors of 2, so 4x squared. Now we're getting better. I can cancel one of these x squared. I can cancel this x squared plus 4 with 1 factor of the x squared plus 4 in the bottom. And so up top we have 16, and then in the brackets this simplifies to 3x squared minus 4. Whoops, sorry. Questions? Yeah.
Where did you get that 3x squared from? Like just
Mhm.
more than anything.
So this, in the line above, if you distribute this negative, you have minus x squared minus 4, and then I just combined this minus x squared and that plus 4x squared. Other questions?
How would, out of curiosity, how would the process for this work if we were to do it with the product rule?
It would work the same way.
Same way?
Yeah, you'd be factoring out, you use the product rule, so you'd have, in one of those, you'd have an x squared plus 4 to the negative 2. And then in the other one, in the other term, you'd have an x squared plus 4 to the negative 3 after you take a derivative. So you'd be factoring out an x squared plus 4 to the negative 3, so you can sort of see where that comes out. If you rewrite it and use the product rule and then simplify it so you can write it as a single fraction at the end, you'll get like precisely the same thing.
Cool.
Okay, so next we want to figure out, do we have any possible inflection points? Let's set this equal to 0. And this is a fraction, right? When is a fraction 0? Yes. So all I'm going to do, and in fact, and you know what's great about 16? It's never 0. So in fact, I only need to look at where is 3x squared minus 4 equal to 0. And we can solve this. There's 2 solutions here. Notice this doesn't like unfoil, right? We're not going to get linear factors out of this, but that's okay. We're going to find 2 possible inflection points. So 3x squared is equal to 4. X squared is 4/3. And then we take the square root on both sides. So we get x is plus or minus 2 over root 3, which is 1.15 approximately. Now notice this, because this doesn't split into linear factors, we're just going to be a little bit careful about making our sign chart. It's not that hard. It won't be that hard, but we just have to be mindful of the fact that there are 2 places where it's 0. The bottom is still always positive, right? Because x squared plus 4 is always positive. 16 is always positive. In fact, since this is always positive and the bottom is always positive, the sign of the second derivative depends entirely on what's going on with 3x squared minus 4. So we can make this sign chart. We have two possible inflection points, minus 2 over root 3, positive 2 over root 3. And we're just going to look at what's going on with this. So we know it's 0 here and here. Because there are two zeros, that splits up this number line into like 3 intervals. So I just have to see what's going on in each interval. If I plug in something less than this, like, so if I plug in like negative 100, what's the sign of 3x squared minus 4? Okay, so we're plugging in like a large negative number, right? So like, let's say I plug in negative 100. If I square that, I get something really big, right? Yeah, I get something big and positive. And then I'm going to subtract 4. It's still going to be positive, right? So it's positive over here. If I plug in something in between, my favorite number to plug in this interval, anybody know what it is?
0.
0. What do we get? Negative. And if I plug in a big positive number, what do we get?
Positive.
Mm-hmm. Nice. Okay. Questions before we look at the end behavior? No. Okay. So let's do that. Let's look at the end behavior. So this was item 4. I mean, I could do item 4 first. I guess there's not like, they don't have to be in this order, but it's sort of the habit that I'm in. So we look at this end behavior. We're going to set up the limit as x approaches infinity of the function. Just the function itself, 8 over x squared plus 4. What happens to 8 over x squared plus 4 as x gets huge?
It's smaller.
It gets smaller, right? If I wanted to get super small, I could just keep letting x get huge and huge. What is this limit equal to? That's not small. It's 0, yeah. It gets small is what we know, right? As x gets huge, I'm just taking 8 and I'm dividing it by huge numbers, right? And on the test, if you look at that second, like I think it was on the first page, you did a limit as x approaches infinity, right? And this is that kind of problem. You know, if it were 8 over x squared, we were really used to just seeing that and be like, oh, 8 over x squared, as x gets huge, that goes to 0, right? Well, if that goes to 0, certainly if I just add 4 in the bottom, that also still goes to 0. So this limit is 0, and what that tells us is that y equals 0 is a horizontal asymptote. So that's good information to have. There are no vertical asymptotes, by the way, and we were able to figure that out straight away. It was like basically the first thing we did. We didn't write that down, there are no vertical asymptotes, but can anybody tell me why there are no vertical asymptotes on this graph?
Because our x domain is all real numbers.
Yeah, the vertical asymptotes only occur at values of x that might make us divide by 0, right? So as soon as we do the domain, like answer that domain question, we will know right straight away that whether or not they're vertical asymptotes. All right, let me zoom out for a moment. See how I'm doing on space. Doing pretty great on space. I'm gonna make this. Yeah. Well, you know, feel you know, I. What? Yes, yep, I'll do that. I think I can fit it all on one page. So now let's organize the information. So this is where we make that This is where we. Yep, it is. I understand. Look, I'm a cheater. Okay, so this is where we make that chart. We're gonna keep track of the interval, the y coordinate, y prime, y double prime, conclusion. So in the values of x that I'm interested in are any critical values, and also places where the second derivative is 0 or undefined. So the derivatives are defined everywhere. So we had one critical value at 0, and then we had these two possible inflection points. By the way, are they actual inflection points?
No,
Why?
because it's a second derivative. It's telling us that it's either concave or convex, but concave up or concave down.
Okay, but
Well, no, that
what
makes
happens
sense.
here?
Well, right. Because it goes from positive to negative.
Yeah, right? The concavity changes. So these are actual inflection points. We're going to need to find those y coordinates. But these are the values we're going to use to kind of cut up the real numbers. So we're going to start at minus infinity to minus 2 over root 3. Then we stop and see what's going on at minus 2 over root 3. Then we go from minus 2 over root 3 to our next value in order, which is 0. That's our critical value. Stop and see what's going on at 0. 0 to 2 over root 3. Stop and see what's going on there. And then 2 over root 3 to infinity. We only have to fill in the first column, that y column, at the actual values. Here, here, and here. We already found that when x is 0, y is 2, so I'll throw that in. And then we just have to plug in 2 over root 3. So 8 divided by 2 over root 3 squared is 4/3 plus 4, and that's 3/2. And if you look at the function, right, the only time x appears, it's being squared. So whatever it is at minus 2 over root 3, that's what it is at 2 over root 3, right? It takes on the same values, positive, negative. So that's 3/2 for both of those. How do I fill in the y prime column?
With our positives and negatives.
Yeah. Yep, we already made the sign chart. So I'm just taking like this right here and just putting it in that column. So it's positive, it's 0 at 0, positive before, negative after. Whoops, wrong column. And then similarly for the second derivative, we've already made that sign chart. So I'm just taking this and throwing it in there. So it's 0 at plus and minus 2 over root 3. It's negative in between and positive on either end. All right, let's do the conclusion column. What do we write in the first row? What's our conclusion?
Concave up.
And?
Inclusive.
Right, so that part of the graph will look kind of like this. You'll have that kind of behavior. What about what's happening at this point? Negative 2 over root 3, comma 3/2.
Maximum,
Y max.
because the plus sign and then the negative sign afterwards.
I would agree with you if that existed in the other column. But that's in the second derivative column. What's that? It's an inflection point because the sign changes. So the sign change tells us something. It's just not a max. It's an inflection point. Next row.
That's your maximum?
Why? What row are you on?
Concave decreasing down.
Say that again.
Concave decreasing down.
Okay, so it's concave down.
Or concave, yeah.
Yep, and increasing. Yep. So increasing concave down, that's like that kind of shape.
And the next one's a max.
There's our max. Yep. And we could tell because we see the sign change in the first derivative. We also see that it's concave down at a critical value. And so that has to be a max. What about the next row?
Concave down, decreasing.
Concave down what?
Decreasing.
Yep. So concave down decreasing looks kind of like this type of shape. Next row.
That's our other inflection point.
Mm-hmm. Good. And last.
Concave decreasing.
What?
Never mind.
Let's take them one at a time. First derivative's negative. What does that mean? Decreasing. Second derivative's positive.
Concave up.
Concave up. Good. So decreasing concave up looks kind of like that. All right, now we're going to sketch it. You guys ready? I'm going to sketch it right here. So we know that the domain is all real numbers. I'm just going to, before I draw my axes, I'm going to just observe that y is always positive, right? So this graph is going to exist entirely above the x-axis. Okay, so it has a max at 0, 2. And then we have these other points. So let's see. I don't think I need to go too far out. The other points were at our inflection points plus and minus 1.15, so that's here, and then the y was 3/2, so that's like probably right around there, and maybe right around there. So there's our max. That's what it does. It's concave down from here to here, as we observed on our table, the chart that we just made. It goes concave down increasing to concave down decreasing. On the left side, this is an inflection point. So here, it's increasing concave up. So it's kind of heading into that point like this before it turns concave down. And now as x gets large, we already found that limit to be 0. So as x gets large, it's just going to start like hugging the x-axis. There's the graph. Pretty fun.
Sure.
Excited for the next one, you know?
Yeah, good. Good. You should be excited. I'm excited. I gotta tell you, this one's pretty enjoyable, but I saved the best for last.
Yeah.
Oh. What the? Okay. Hold on. I didn't print that page.
Don't do it. It doesn't exist.
You know what? It exists. How did I do that? Okay. Whoops. Let's see if I can print current page. Okay, let's see if this works. Okay, here we are. Don't worry, guys, we figured it out. Okay, let's get to graph of this. What comes first? What do we do first?
Find intercepts.
Yeah, I would say okay, let's find the intercepts.
You don't have to.
So let's find the Y-intercepts. Intercept.
Step one, don't leave.
Oh, that's
Okay. Well, you know, I think it was intercepts is a fine thing to think about. In fact, if we thought about the intercepts first, we say what's the Y-intercept, and then we get stuck because we've learned that 0 is not in the domain, right? So the domain x can't be 0. And if x is 0, that makes us divide by 0. We have a vertical asymptote at x equals 0. Now intercepts. What about the Y-intercept?
There is no Y-intercept.
Yeah, 0 is not in the domain. For the X-intercept, we're going to set y equal to 0. So 0 is equal to x plus 4 over x. If I'm solving an equation with fractions, I just clear denominators first, usually just as a matter of course. It makes it a little bit easier. So I multiply through by x. And if I do that, then on the left side we get 0 still, and on the right side we get x squared plus 4. When does that happen? What?
Never.
Never. Yep. So never happens. No x-intercept. So what we know so far is that we have a vertical asymptote at x equals 0 and no intercepts. We got no points so far. Feeling pretty good? Good. All right. We're not going to let that get us down because we have some calculus to do.
So why did you just leave it at 0 equals x squared? Why didn't you subtract 4 over and solve for?
Why didn't we? Okay, so if I subtract 4, what's the solution to that equation? Yep. These are real valued functions.
I know.
So, yeah. All right, let's get our derivative information.
I know.
So to find the derivative, I'm going to rewrite this. X plus 4x to the minus 1. No product or quotient rule needed, right? Just a nice, simple power rule. What do we get for the first derivative?
-4.
No.
X to the negative second.
Okay. What comes first?
1.
1. Yep. Now, I'm going to take this up here. I'm going to keep working with it. If we want to make a sign chart, we need to go back into fraction mode. And we want to be able to write it as a single fraction. So That's 1 minus 4 over x squared. And if I get a common denominator of x squared, this is x squared minus 4 over x squared, which we can factor that top. X plus 2. X minus 2 over x squared. That is something, oops, my prime. That's something we can make a sign chart for, right? Can't make a sign chart here, but I can make a sign chart here. So we'll have a row for each of those factors that appears in the top and the bottom. And then the last row for the derivative itself. Critical values.
-2, 2.
And 0, because critical values happen not just when the derivative is 0, but also when anytime the derivative is undefined. And so if x is 0, that makes this undefined. So I'm going to use all three of these when I make the sign chart. Got to put them in order. So -2, 0, 2. X plus 2 is 0 at -2. Negative on the left, positive on the right. X minus 2 is 0 at 2, negative on the left, positive on the right. X squared is 0 at 0, but it's positive everywhere else. And now in this bottom row, I want you to just sort of look at how I'm indicating this. At -2 and 2, the derivative is 0. At 0, the derivative isn't 0. So I don't want, like when we focus first on polynomials, it can become almost automatic that if I grab a 0, that just makes it a 0. In fact, it's undefined. Usually I write that or indicate that just by putting like an open box or something. But like the function doesn't exist there. And then fill in what signs go in here. Positive.
Negative.
Mm-hmm.
Negative.
Mm-hmm.
Positive.
Yep. Good. So there's our there's our first derivative information. Let's move on to the second derivative. Now we have the first derivative, right? Here's the first derivative as a fraction. Here's the first derivative as a fraction. Those are great. I really wanted it in this form because that's what is helpful for me to analyze. But if
How did we get x squared minus 4 over x squared?
So this is
Oh, the quotient.
get a common denominator. Yep. So this form, is great for making the sign chart. We really needed to do that. But if I'm finding the second derivative, I'd rather not start here. In fact, it's much easier to just use this form. This is convenient for taking the derivative. So that's what I'm going to do. What do we get for the second derivative? 8x to the minus 3. And then I'll write that as a fraction. 8 over x cubed. Much easier. Like, see how little work that took compared to if I had started here or here. So think about, like, you get to decide, like, we're trying to make our work as easy on us as possible. So think about that, keep that front of mind, like, as you're kind of going through this, these types of problems. Where is the second derivative equal to 0? Well, it's undefined when x is 0.
So other than that,
Nowhere, because 8 is not equal to 0, right? So y double prime is never 0. What does that tell us about the graph? No inflection points. Our sign chart, it will be fairly simple. There's no possible inflection points, but I still have this point of interest at 0. I always want to include the places where that derivative, or first or second derivative, is undefined, because you can get different behavior on either side. And in fact, in this case, we will. It's x cubed, right? We're raising x to an odd power, so it's undefined at 0. But what are my signs? Like, what do we get if we plug in a negative? And if we plug in a positive? So even though there's no inflection point, we will observe a change in concavity.
Okay.
Just going to happen on either side of this vertical asymptote that we've already identified. Let's talk about the end behavior. This will be interesting. We want the limit. We want to find the limit as x approaches infinity of x plus 4 over x. So now, as x gets huge, what happens to 4 over x?
It's smaller.
Gets smaller, and then this gets huge, right? So overall, what happens? It gets huge. So this limit is infinity, but we're going to be more specific, all right? So what the takeaway from this observation is, since 4 over x approaches 0, right? The reason that this approaches infinity is because x approaches infinity, right? Because of this term. And what that means is that as x gets huge, the behavior of the graph starts to approach the behavior of just y equals x, right? This part becomes insignificant, and this takes over entirely as x gets huge. So for that reason, what I'm going to do is I'm going to say that this limit is x. Yes, it is infinity, but what's going to be helpful for me is to understand that the behavior is the same as the behavior is x, of x, y equals x. So this is a slant asymptote. Y equals x is a slant asymptote. A graph can have a horizontal asymptote or a slant asymptote. It can never have both. It can sometimes have neither. But we figure that out by looking at that limit and trying to see whether it approaches a fixed number. Then it's a horizontal asymptote. If it blows up, we want to ask, how does it blow up? And in this case, it blows up just the same way that y equals x does. So now I think we're ready to kind of organize all of this information. So we're going to write down the interval. A y column, y prime column, y double prime column, conclusion. The points of interest that we had were at -2, 0, and 2. I think that encompasses both the first and second derivative. So my first interval is from minus infinity to -2. See what's going on at -2. -2 to 0. See what's going on at 0. 0 to 2. See what's going on at 2. And then from 2 to infinity. How do we start filling this out?
Find y when x equals -2, 0.
Mm-hmm. Yep, so that y column only got to be filled out for those fixed. Now, at x equals 0 is not in the domain,
Yeah.
so I'm just going to put some, like, cross out and just write down here. That's where we have our vertical asymptote. So we just need to figure out what is y when x is -2 and when x is 2. So when x is -2, I'm going to scroll up so I can see the function. It's x plus 4 over x. So at -2, that's -2 plus 4 over -2 is -2. That gives us -4. And when x is 2, we have 2 plus 4 over 2, or 2 plus 2. So I think at negative 2, y is negative 4. And at 2, it's positive 4. So we have 2 points. All of this so far, there's only 2 points. And we know there's no inflection points. We're going to plot 2 points and then use all of our observations to fill in the rest. So the y prime column, we were just going to grab that from the sign chart that we made. So plus, minus, minus, plus. Like that, at 0, at 2, and negative 2. For the second derivative, it was negative on the left side of the vertical asymptote, positive on the other side. What are our conclusions?
The first is increasing convex down.
Concave down, yep.
Concave down, sorry. And then we have our maximum.
Yep. Decreasing concave down. Next. You're ready to go.
I filled this out already.
Okay.
You want me to answer?
Yeah.
Okay, so the next one is going to be your, not the max, minimum. Yeah, minimum.
Well, what about this row that I'm at right now?
Which, you're at the 0 row. I just crossed everything out like you did.
No, I'm at this row. There's not a 0 here.
Oh, that's a concave down increasing.
Nope. Decreasing
You're like tricky.
concave up.
Yeah,
What?
okay.
No, no.
Wait.
He,
Oh.
he had the switch.
Okay. Then what?
Oh, I know. Now it's the
That's a minimum. Right? It's concave up at a critical value. And last row.
concave up increasing.
Yeah. Don't sound so sad.
Must have missed that row.
Okay. All right, now we're going to sketch. Did you sketch it too, Aaron?
No, I didn't.
Yeah, okay. This is the fun part, though. Like, I just don't understand. Like, you're doing all this work and then you're not sketching the graph?
Well, you see, I'm not.
You're not super into this. I get it, yeah. Okay, so we have, let's see. 1, 2. And then the max and the min were at 4 and negative 4. All right, so here's what we know. We know that y equals x is a slant asymptote, so I'm sketching that in. Dotted line. I know it goes to the point 2, 4, and negative 2, negative 4. Everything else, we're just going to figure out by piecing this together. We also know that the y-axis is a vertical asymptote. When a graph is approaching a vertical asymptote, it can do one of two things. It's either going to shoot downward towards negative infinity or shoot upwards towards positive infinity. So if I think about what's going on here, so it goes to this point, right? And there are no X-Intercepts, we've decided, right? So already, that should tell us that it's going to shoot downward. It could not possibly shoot upward as it approaches this without it crossing the x-axis. And it doesn't do that, right? We already determined that. But not only that, we know that it's increasing into this. There's a max, and then it's decreasing coming out, and it's concave down this whole way. So this behavior is going to look like this. There's our max, like that. And then this y equals x is a slant asymptote. That means that as x gets huge, it just starts approaching that line. On the other side, goes through the point 2, 4. As it approaches the vertical asymptote from the right, it's got to shoot upwards. Like, first of all, this is a min, So it's decreasing into that point. So it's got to do that, right? Then it turns around. It's concave up the whole way, right? So, and then it's increasing forever, increasing and starting to approach this y equals x line. So there's the graph of this one. We plotted just 2 points, but we were able to kind of fill in all the in-betweens. How's that? So good. Yeah.
Maybe a silly question. Will the slant asymptote always slant that way, or could it slant it the other way?
It could if it was y equals negative x, right? So we found that y equals x is the slant asymptote, so I just graph that line. There's a slope 1, positive 1, that goes through the, 0, 0.